Okay. Alright, Assalamualaikum warahmatullahi wabarakatuh. So, good day everyone. Okay, so today we're going to continue with we have covered deflection in our last lecture. So we're going to continue with what we call as end block. So as I said again, alright, so end block is what we call that is not in your syllabus. So I will just go through it very fast just to introduce you few terms and what you have to design, and then just show you, in one look of the example and the design part. So it will be very quick overview of end block, because actually end block is one part of design that you must carry out, when you design pre-stressed beam. So that's why I don't feel it's right when we have to omit end block design. So since that is not in your syllabus, I will just here to let you know what is end block. Okay, what is end block, and then what actually we design. Okay, all right. The rest you'll be able to explore it later on by yourself, if you need it. There is the skill. Okay. Oh, maybe I should, because we already covered deflection, right? Okay. So end block. Okay. So what is end block? Right. So I think that's the most important question that you guys need to know. Okay, so in a pre-stress force, all right, when it's in post-tension, especially post-tension members, when you apply load after concreting, right? Okay, so when you apply, actually you are kind of like concentrate your force at certain point, okay, on a small area at the end cases where you place your jet, and then you want to pull your tendon. So basically there are already a concentration of stresses or forces at certain location where you apply your jet. Okay, so that part, if you didn't design properly, that particular part that near to the area is where your structure might fail. Okay, it might burst out, it might rupture, it will crack or something like that. Okay, so we want to avoid that thing to happen. So what can we do to avoid that thing to happen is by design that particular part where you call it as an end block region. Okay, and then having a certain specific reinforcement to it, because when you design, of course, we say design means we determine the section, the size, you provide sufficient, what will be the reinforcement you want to provide, the area of the reinforcement you want to provide, the placement of the reinforcement, and what we call that, how many, and so on. So that's what we're gonna design the end block part. Okay, so here if you look into the what we call what's written, you can read it generally by yourself. Okay, it's not that good. Sorry, a bit flu. Okay, so this region is known as end block and must have heavily reinforced by steel to resist a bursting tension. Okay, so you have to have a sufficient strength at the end block. Okay, because you are applying, quite a great what we call force at that part. So end block reinforcement generally consists of, so reinforcement, what kind of reinforcement that you want to provide? It could be close link which surround the anchorage, and the quantities provided are usually obtained from empirical method. So we design in terms of providing reinforcement. Okay, did I miss anything? Okay, hopefully no. So anchorage, I think by now you should be able to know what is anchorage. Okay, why my slide is not moving? Okay, all right. So here will be the failure due to uncontrolled cracking or splitting of the concrete from insufficient transverse reinforcement. Okay, so normally if say that you didn't provide sufficient, if you didn't design properly your end block, so then your anchorage zone failure, excuse me there. sorry, yeah. It was such a flu. Okay, because I didn't, move away from the screen and from this setup. You will be, it will be sounded very loud in the video. Okay. Okay. All right. Where am I just now? Okay, so you want to avoid the anchorage zone failure to happen. All right, so because when it happened, then it will burst out and so on. So it's something that you don't want it to happen. So another failure that it could also occur will be what we call as bearing failure. Okay, so it will happen. Sorry, behind the anchorage plate are also common and may be caused by inadequate dimension of bearing plates and poor quality of concrete. So the plate itself, okay, didn't be is not the dimension is not properly designed, and also because of poor workmanship during the concreting. So here is where you would see common what we call that anchorage. This is the anchorage part. Okay, you could see this, and then you will see this square. That is what we call as the plate, okay, of the anchor. And then if you look here, this part, you will see like a reinforcement outside here. There are some of it. Okay, so this is where you design the front part of your what you call your block. Okay, it's the end block you design. So this is another picture of, you can see it closer. This is the plate, okay, and then this is your anchor, okay, where it holds all your tendon. And then if you can see, this is a very clear picture. This is what we call as a wedge. Okay. Okay, and what you see here, okay, this part is all the reinforcement provided. Okay, reinforcement provided that you what we call that provide at the end of the beam, okay, for the end block. Okay, just because you're gonna pull the tendon, can the anchor out, so it has to have a proper reinforcement. Okay. All right, so this is just to show the angle of where you apply the load. Okay, I just want to highlight this. That one you can go through yourself, because it's taken from the book. It is just to verify the, what you call that? Okay, just to verify you the 33.7 that we're gonna use later on. I will show. Okay. So here you have two possible condition. So one will have, like we call a single anchor plate. So you have one anchor only at the section. So here you have what you call as double anchor plate. Okay. So this double anchor plate is where you have two. Of course, you have two anchors. So this one you have one. So you can see the pattern of how the stresses distribute along the length. Okay, this one is like this. So the concentration part is this part. This is the concentration part before it's being distributed, along the length of the beam. So we want the design, normally we want to make sure that we design appropriately at this part, because the concentration is at that particular part. Okay. So your end block design is based on this formulation. Okay, taken from the code. And your AC node and AC1. So AC node is the area of the anchorage plate. So the plate that I've shown you before. Okay, and then the AC1 is the maximum area. Alright, same shape as the AC node. Okay, having the same shape as AC node, which can be inscribed in the total area of AC, which is the concrete area. If you look here, this is actually AC1. This is AC node, and then this is AC. Okay, so that's more or less. And then this is the theta of how the load is dispersed. Okay, we are taking consideration the dispersion is taking about 33.7 degrees. Okay, this is as empirically studied by the code, provided by the code. So we take the partial safety around 1.2. Okay, disperse angle. Compressive strength should not exceed this. Okay, these values as stated, and then the reinforcement is designed at 0.87, limited to 3,300 Newton mm per square. So no crack check is necessary. Okay, so a deviator shall satisfy the following requirements. So you can just go through that later on. Okay, and here is the distribution. Okay, when you have a flat anchorage, or this is conical anchorage, in terms of conical anchorage, it's a different type of anchor actually, so it will give you a different type of stress distribution here. Okay, all right, so this is the part where you want to consider the end block design. Okay, if you have a flat anchorage, so you want to design this part. Okay, from here to here, so the length is around 2.0 y naught. So y naught, this is also 2.0. So the section is always normally in a square. Okay. Okay. So here the reinforcement. When you provide reinforcement for your end block, so it must be designed to withstand the bursting tension. Okay, so which is determined by the transverse stress distribution on critical axis, usually coinciding with the line of action of the largest individual force. So you want to avoid it from bursting because you are pulling the tendon with a very high force. Okay, so you want to avoid that particular part near the anchorage from bursting. So we have plate, or we call as embedded fry sinet type anchorage. The typical arrangement of reinforcement in end block figure 5. So normally the arrangement is something like this lah. You have like this the anchor, the wedges, and then this is the lock. You cannot really see this one. Okay, something like supposed to be, because the picture is a bit blurred or something like that. Okay, all right. So mat helix loops links are generally provided in perpendicular direction. I think you have seen that before. Based on research work, helical reinforcement is more efficient than mat reinforcement. Okay. So here is the type of where you have the reinforcement provided at the end block. Okay. Okay, and then you have also what you call as a hairpin bars. Okay, this is the link as the mat. Okay, how it looks like. Okay, so the example here is to show how you can design your what you call end block. So the end block is designed with 400 times 400. Okay, so you have this is your anchorage, your tendon. You have 4 tendon. So this is kind of like your plate. Okay, so 100 mm diameter conical anchorage located at shoot. Jacking force 250. So they may be provided into 4 equal end zone. 200 times 150 each. So determine the reinforcement. Oops, why my pencil have no battery? Oh, no battery. Okay, determine the reinforcement required around anchorage. So with the parameter given, so consider as one anchor. So we have one anchor. Okay, see one anchor lah, one part. Oops, sorry. So here you calculate the actual actual bearing stress. Okay, by taking what is the force, multiply with the parameter with the what you call the partial safety, divide by the loaded area. So the loaded area will be 100 Power of 2 divided by 4. This is the what we call the tended area. So the loaded area lah, one loaded area. So 38.2. Okay, and then you have the allowable. The allowable is around 40.2. So you check the one tandem with the allowable of 1 as well. Okay. Okay, that's one thing. Why 150 and 100? So we are talking about 100 here. Okay, we are considered as a circular as well, as you can see before, the slide before. Okay, and then the 100 is the tendon size. Okay, so for the reinforcement, so the tensile force, so we use the concept of the tie. So we are considering this. So 0.3, 3 times 1.2, where you get 250, where you get 100 kilonewton for this. So the area of the tensile is where you take into consideration of your tendon area. Okay, and what we call that, the force here, the force that you get for the tensile force divided by 300. Okay, 300 is where you get your what you call your stress value. Okay, then you get the area is around 330. 300 is the the stress value. Okay, and here is where you have this can be provided by 10 mm close link, which is, we say from here, you say that 300, so say that we provide like 471 mm square. And then this is the spacing from one link to another link lah. Okay, so then distributed over a length equal to the largest dimension, which is around 200 mm. So we provide it the block about 200, the largest dimension, which is 200. Okay. Sorry. Suddenly you feel not well, block. The previous class is okay. Okay. There are two legs of each link acting against a tensile force. So as I said, we go very fast lah here. Okay. Not really detailed. So if you look here, you can see that the section is designed according to the strut, taking into consideration of the position of the force, which is 33.7 degrees. So you will get the stress in the strut, and with the stress in this which is around 7.12. Okay, so with this, you kind of calculate what is the tensile force, okay, by considering 1000 kilonewton precise force acting. Okay, and then about 400, now you estimate again what will be your tensile steel required. Okay, all right, so that's it. So it will provide 12 and then you can conclude lah what will be the reinforcement actually that you want to provide, and then is it sufficient or not, and then do the checking. Okay, all right, so yeah, that's about the pre-stress the end block. Okay, any question about end block? Not much. I mean, I don't really go detail, for example, so it's just a go through. Okay. 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 Fatin, okay?
Okay, madam.
Supri, okay?
Okay, madam.
Right. So at least I know it's not much. I know it requires much more explanation. But at least you know what is end block, where is it, and then why it must be designed. Okay, and then at least you know what kind of reinforcement that you need to provide. So if say that you require, if you need to deal with it, at least you know you have some notes on it, and then you can at least start from there lah to work out the design. Okay. All right, that is only my intention, not really for you to break your brain to understand it. Okay. Okay, so yes. All right. Before I go, just quick reminder. Especially, I noticed yesterday. Before that, I didn't put yet your deflection assessment. Yesterday, I didn't manage to do it. So, inshallah, after this, I will do it. Okay, and submit your deflection assessment because I'm about to really nanti later kena have to release something about bending moment as well. Okay. Okay. Uh, about the attendance just now. Okay. I noticed that some of you scan your QR code for your attendance. Okay. But please aware when you say that, because when I look into the timestamp of your your Google form, some of you like stamp it like right away. For example, like you already scan QR code at what is the time now? Today, now is like 10:33, for example. And then you say, okay, which topic, and then which medium. Say that Microsoft Team. Sorry, online, Microsoft online kan, video ke apa kan. And then 10:34, 1 minute later, you scan it again. And then you said you are you are in OneNote. Okay, please be careful about that, because I know I'm trying not to be rigid, but of course I also want it to be, the data must be reliable. All right, means that it's not doesn't make sense when you study about one thing, okay, and then 1 minute later you study about other thing. Okay, in terms of reliability, it's not that it doesn't make sense a bit about that. So because when you scan QR code, it actually means that you go through the notes, you do some reading, you do some studying, if you scan the note on your assessment, means you are doing assessment, means you are using your OneNote and things like that. So that's supposedly reflect your participation or your activity, what you do related to related to the course. Okay, so but when you do you scan the QR just for the sake to capture at least 2 times, and then you scan it like very close to each other, like 1 minute gap, 5 minutes gap, so it doesn't make so much sense. Okay, because for one video lecture pun normally to finish around 1 hour kan. Okay, so when you means that if you stamp it right away after that you open OneNote, means that you didn't really watch the video, so it already reflect negatively on you. Okay, so please watch out on that lah. Okay, because I know when people or when anyone check your attendance and look into your participation, and then the data is not that reliable, so it easily can be questioned in terms of your participation. Okay. Okay, all right. So yeah, that's about that before I forgot. Okay. All right, so let's move on. Okay, before that, give me 5 minutes to clear it. Okay, all right. Sorry. Okay. Not easy giving 4 hours lecture during Ramadan. Okay, so let's proceed then, inshallah. Okay, so ultimate bending strength. Okay, so for this topic, actually, it's not something new for you guys, because it's actually more or less the same thing. with what you have done in your RC design. Okay, so please check your RC design notes just to recall back, you know, your maybe you forgot how to design in terms of bending moment and all. Okay, you can recheck back. Okay, that's one thing, right? Okay, in terms of topic outcome, at the end of this topic, students should be able to determine bending capacity of the pre-stressed concrete beam. Okay, so today for at least like maybe 1 hour or less than 1 hour, so now it's already 10:30. So maybe we stop like, maybe I try to stop like probably 11:15 like that. Okay, we will cover in terms of how we want to check our beam. Okay, in terms of bending capacity. So for you guys, for you to know that at this point, okay, let's just show you this one before I proceed with the bending moment for you guys, so that you guys not confused. Where is it? Okay. 5. Boleh lah. Okay, so at this point, what we have already, okay, if we refer back to our 4 basic inequalities equation, okay, at transfer and also at service, okay, you will notice that what we call, okay, we already have our P naught, pre-stress force that you want to use, because we determine it from the Magna diagram. Okay, means we choose. We have the range, Magna diagram give you a range, so you have choose what will be your pre-stress force value that you want to use for your pre-stress beam. And then we know already the E, the position of the tendon, where you want to place your tendon. And then your area, so this one you already determined earlier, your section size that you want to use. Okay, and also the rest. So when you include all these parameters inside this equation, basically you will get the actual stress. Okay, the actual stress at the top and also at the bottom at transfer. Okay, so what you before you know all the parameters, you don't know what is your pre-stress force and you don't know what is your eccentricity. So in terms of to know your pre-stress force and eccentricity, you equal your equation with the minimum. Means that you take all the values, the maximum and minimum values, the limiting values of the equation as stated in the code. Alright, so means that by taking the minimum and maximum value of the stresses up on top and bottom, it will give you what will be the optimum value for your P naught and E. Alright, so when you already decided how much P naught that you want to use, how much E, the location of your E that you want to use, so basically you can put it back and then you can recalculate what is actually your actual stress that will occur at your beam at the top and also at the bottom. At both conditions, means at transfer and also at service. So at service, you have to consider the K value, the losses that might occur as well. Okay, so you will get what will be your top stress and then what will be your actual bottom stress. Okay, so this will represent the stresses that will act on your beam. Okay, so of course it will satisfy this condition, means that it will be lesser or equal to F maximum, it will be bigger and equal to F minimum. So normally when you already determine your P and your E, you put back into the equation and then you will check either is a bigger, it satisfies the equation or not. It must be bigger, lesser than F minimum, lesser, equal than F maximum, lesser and bigger than F minimum. Okay, so that's what happened. Okay, so when you know it's already the stresses that occur on the beam is okay, fulfill the equation, so then you know that okay, your design is sufficient in terms of what you call serviceability limit state. Okay, and then of course after you check your deflection and all. Okay, but another stage of pre-stress beam is to check against ultimate limit state. So against ultimate limit state is where you're gonna proceed with what we call that with the bending check. Okay, so that is what we're gonna do today. Okay, right. Then I can proceed with bending. So hope you guys are clear with the process. Okay, so at the end of this topic, students should be able to determine bending capacity. Alright, so I think in pre-stressed concrete design, structures are generally designed at serviceability limit state. That's what we have done. Okay, however, it is stated here, it is equally important to ensure that the design structure has sufficient moment and also shear capacity at serviceability at ultimate limit state. So you don't design against moment you don't design based on ultimate limit state, but you have to make sure that your design structure is sufficient against moment and shear at ultimate limit state. So the partial factor of safety on loads, okay, and materials are similar to the RC design. Okay, so however, the effect of the pre-stress force need to take into account. So this is where you will take note. Oh, sorry. Okay, take into account. So there's not much different between the design. All right, the design is still the same. It's just the effect will be, maybe the condition of it will be slightly different. Okay, so what I will do today is, I think most of it will just kind of like recall what you have done before. So the force should multiply with the factor of safety, which will take 0.9. Okay, so ultimate limit state. So we have ultimate moment resistance, and also you have shear resistance under uncracked and also cracked section. Okay, so those are, you have two conditions here when you design under ultimate limit state for pre-stress. So load are factored as in accordance to EN 1990, the same. Okay, where you have 1.35, 1.5. Okay, this one for your QK and also for your GK. So I will not go through it in detail. You can look into it's the same practice. So material properties. Okay, so this is what probably a bit need, because you have additional of tendon. Okay, in your design, in your bending moment. Okay, you have strength type, standard, super, or drawn. So this is the type. So you have the diameter, you have the FPK, the strength. This is after the 0.1 relaxation. So you have P naught, what is the force, and what will be the maximum. Okay, for each type of the strength. So each type of the strength, it has a specific, force that you can apply. Okay, so this is as what given. So where to get this value, where to get this table? Okay, this table normally you will get it like from your manufacturer. Okay, that provide you the tendon. So they will give you a range of what will be the type that they sell, that they have, and then what will be the range of diameter that they produce. So each type of the strand will have a specific material properties lah, and then what would be the forces that can be applied, what would be the maximum. You cannot go beyond that maximum. If you go beyond that, it will fail. Okay, your strength will fail. So this is the concrete. I think this is a common one where you have concrete strength 30, 35, 40, or 50, and then what will be your FCK, and then what will be your modulus. Okay, so the thing about to design the what we call the moment, or to check the moment, so you have to analyze the section, because as we know, for pre-stress beam we have additional tendon, so we have to analyze the section first before you can know what will be the sufficient moment to provide. So a pre-stressing steel begins to behave as conventional reinforcement when loads on pre-stress beam increase above the working values and cracking occurs. Okay, so the behavior of pre-stress member at ultimate limit state is exactly as the conventional reinforced member, except that the initial strain in the steel must be considered. Okay, so when you design, okay, your RC member last time, okay, using especially using the stress block, okay, uh, it's the same procedure, it's the same process, except for you for pre-stress you have initial strain. Why you have initial strain? Because your tendon, you consider steel as your tendon, so then it has, like, it's being pulled, so you have the initial strain, it has already moved, okay, it's being pulled. So reinforcement bars can be used if tendons are insufficient to provide shear and bending moments. So at this point, because tendons, providing the tendons, because we don't design tendons to cater any moment, okay, but then by applying the tendons, sometimes it's enough to only have the tendon and it's sufficient to cater the moment as well. But there is a condition whereby having the tendon, you still need additional reinforcement to cater the moment. Okay, so that's why before you provide additional reinforcement to cater the moment issue in your beam, you have to check first. Okay, is it the tendon sufficient enough or insufficient? If the tendon is sufficient, means that you do not need any additional reinforcement bar to cater the moment. If the tendon is not is insufficient, so then you have to add. Then you have to design lah. You have to add more bars to cater for the moments. Okay, so that's what we're gonna do exactly. All right. To calculate tension forces in each layer of steel. So in general, we have total steel strain is strain due to bending and initial strain. Okay. So when talking about tendon and having tendon in the beam, actually, especially pre-stress tendon, okay, we have what we call additional of strain. That's why the steel is not strain due to the load only. You will have additional, we call as initial strain, due to the pre-stress force applied. Okay, so tension capacity is compared to the compressive force developed by uniform stress of 0.567 FCK. Okay, so by using the concept of equilibrium, the moment of resistance can be calculated. Alright, so in this case, we will use the concept of what we call in equilibrium equation of tension capacity and also compressive capacity. Okay, so we're gonna utilize the what we call the stress block condition. Okay, all right. For those who are not familiar with what shown in the slide, I think this is about it's a time where you have to recall back later on. Okay, before we proceed, because today will only be a briefing on the lecture or in the theoretical part. So if you're still not clear, you have to try to recall your notes. Your notes in terms of in your RC design. Okay, because there's like more detailed explanation in terms of that to understand about compression zone, tension zone, equilibrium, and so on. Okay. Okay, so if you look at this, right, it will take a while for me to to explain this. So what you see here is actually a two main symbol, which is the lambda, and also this is what we call as I always call it as a mu. All right, so this is the coefficient actually that multiply your XCD and also your X, means your your block height. So your first we took into your lambda, which is it varies 0.8. Is it the value taken as 0.8 or 0.8 minus FCK minus 50 divided by 400. So you will take it 0.8 when your FCK is lesser or equal to 50 MPa. Right, when you use a concrete strength, maybe 40 or 30, then you can take your lambda as 0.8. Right. If say that your strength of your concrete is more than 50, but it's lesser than 90, then you can take it as these values. Okay, that's one thing. So these values varies because you look here, this is your neutral axis of your section. Okay, so normally you will take this one is like your height of your block to the neutral axis. So normally you will take like 80% of the height of the total height that represent for your stress block height around this for your compression. Okay, all right, so that next will be your mu. Mu here is for the width of your block. Okay, because your block will be height and then we have width. This is your block. Okay, so this is the width, which is you have your mu FCD, and then this is the height, which is your lambda times this here x. Okay, so this is like kind of like what you want to determine the size of your stress block. Sorry, excuse me. Okay, so for your mu, so I hope you guys still with me, yeah. Okay. Kan masing-masing, you know, I don't know what you guys are doing over there, the other side of the world. Okay, so at least because it's a very important part in terms of trying to understand the stress block, because if you don't understand this, it will be difficult for you to understand the topic and the example later on. Okay, all right, so please, I know you can rewatch later, but don't let me hanging alone by myself here. Okay. Alright, so here where you once you know which for example that mu is equal to this condition, and then when the FCK is more than 50 or lesser than this, you take the mu as this one value. So with that, you will able to know what will be your width of your stress block and also what will be the height of your stress block. So FCD, what is FCD at this point? So FCD can be taken as equal to 0.567 FCK. Okay, that is your FCD value. Okay, and then this is the compression, because why you need the stress block? Stress block will give you the direction of your force for your compression, which is normally half of it, half of your stress block height. Okay, so that's why it's important to know what will be the height of your stress block. And you normally you have like compression at this side and you have your tension at this side. This is for tension, cater for your steel. So if you have your steel like one line like this, then you have one force. If you have another line like this, so then you have another force. Okay, I think we covered this in your in your RC as well. Okay, so this is mostly this is the stress block. So this is the strain block. So strain block, you consider it this part. So it will drawn accordingly to the neutral axis. Means that it must cross the neutral axis, then you get what will be the actual triangle. And then here is the limitation of your concrete strain, and then this will be the limitation of your what we call steel strain. Okay, right, so let's have a look. So distribution of strains and stresses across a section in bending. So for RC bending theory, assume the concrete will crack in the region of tensile strain. Okay, we assume that. Okay, we assume that cracking will crack in the region of tensile strain. So when there's a tensile strain, then the concrete will crack. So after crack occurs, all tension carried by the reinforcement. Okay, that's one thing important, because tension, we know in RC members will always be catered by the steel reinforcement. So plane section is assumed remain plane after straining. So there will be no changes in terms of planing, because when you strain, actually there will be a skewed a bit movement. Okay, but then since that we don't want to make it as an issue when you design, so we are consider there is no movement, mean it stay like that even though it's being pulled. So that linear distribution of strain across section can be considered. So we don't want it to have like, you know, non-linear value. Okay, so when you have here, okay, this is a typical cross section. All right, so you will have AS compression, sorry, tension, then you have the A dash for compression part. Okay, so here say that the neutral axis that you get is actually somewhere here. You have to determine first your neutral axis. What is your neutral axis? Okay, when you have, because when you have your what we call tendon, your reinforcement, your neutral axis is no longer will be stay at the mid height. Okay, so at this point where you have two different reinforcement, one is this the tendon bottom, and then you have the tendon on the top. Okay, so you have something like this. Okay. And this part value, let me just change the color. Okay, so this part value is actually this ECSC, means that the strain of steel at compression. S is stand for steel, C is for compression. This one is S stand for steel, and this T is stand for tensile. So the strain of steel at tensile, this is strain of steel at compression. So this one is the ultimate concrete strain. Okay, so you have the X value, this is the X. Okay, the length of your you know, the depth, okay, of your height of your neutral axis from the top. Okay, so here is, because in general this is your strain, bending strain. Okay, not much issue about strain. The issue is about what you call that, the stress or the force diagram, the stress block. Okay, the stress block means that this block. So in general we say that it has triangular, so issues like this. Okay, but then the most accurate block, it will be rectangular, like this. Rectangular, something like this. Okay, so anything it's like parabolic, it's not, you like rectangular parabolic, it's not really straight, kan? So in terms of to simplify the thing, we consider it as equivalent rectangular. So that's why you cannot take actual height of the X. You have to have a certain percentage of the height, which is 0.8, 80%. 80% of the X, or the height of your neutral axis from the bottom. So that one is considered as the height of your stress block. Okay, so this is for your stress block. Okay. So here is just a what we call explanation on the triangular stress block. When the stress are very nearly proportional after standard working condition. Rectangular stress parabolic stress block. Okay, within a plastic way associated to the design. So normally we consider these two. So simplified. This one is the simplified version. Okay, simplified version of the rectangular parabolic. Then we end up with rectangular. Okay. So tensile force, you have for B, H, X. So I hope you still remember in terms of calculating your, you know, your your stress block, because we are taking into like count, you know, your triangle, your height of the triangle, the big triangle, the small triangle, and all, right? So for example, like tensile force, here you have B multiply, this is the B, so sorry, okay, and H minus X, so then here this is H minus X will give you this. Okay, and then you will have like, you know, minus okay, minus times with FCT divided by 2. Okay, so this is where you get the tensile force for this one, or when you convert it become what you call that, the force. Okay, simplified concrete section. Okay, so then we try to go to stress strain relationship of a concrete. Okay, before that is the stress block. Okay, so concrete behavior is parabolic. So this one is taken from the, what we call that, from the standard. And the strain is up to, you know, C2, which is this one. This one is C2, 0.02, 0.02. The ultimate design stress is can be taken as 0.567 FCK. I hope you are familiar with this thing. So the ultimate design stress is this value. Okay. This value is actually taken 0.85 divided by this, then divide by 1.5, then you get 0.567. So this is actually 0.567 FCK. So this is the ultimate design stress that we use for our design. So it cannot, the stress of the concrete cannot go beyond 0.567 FCK. Okay, so factor 0.85 allow difference between the bending stress and the concrete cylinder crushing type. So gamma is 1.5 is used. So ultimate strain 0.035 here is typical for concrete grade 50 or 60. So this is the ultimate, okay, which is 0.03. Okay, so next will be, so far, any question or not before I proceed? Question. Okay, Q responding. Aina, Shakira, okay with the block so far?
Yes. Okay, madam.
Okay, yeah.
Okay.
Recall back, your stress block ni in your RC design, because it has been covered in RC design actually. Okay, in detail, because you have to do like, you know, big triangle equal to like small triangle and so on, can then you get what is this value and what is this value and on. Okay. Allah. Okay, reinforcing steel. So the same thing, still like, you know, your RC design. So behavior analytical in tension and compression. So behave linear in elastic range up to the design of FYK gamma S. Okay, where you have elastic range of elastic modulus multiplied with your strain. So then you get what will be your stress for your steel. So in this case, you will take into consideration of your FYK divided by gamma S as your stress steel. Okay, this is the ultimate stress, your ultimate stress lah for your steel. Okay, divide by the properties of you know, your what you call that, your modulus. Right, this is your FYK about 500, depends on the steel grade that you use. Then you will get your strain. So in this case, you will get your what you call tensile strain, tensile stress, tensile strain for steel, which is you conclude divide by this 1.15. Actually, it's the same. So then you will have this 0.7, 0.00217. So something like that. So maybe like here 0.0.0217. So this is actually strain. Okay. All right. So relationship between the depth. Oh no, sorry, you are not clear. Okay. Relationship between the depth of neutral axis and the maximum concrete strain. Okay, which is the strain C2. And the steel strain C2 is 0.00035 kan. This and the steel strain is given as this. So you have this equation. This is the steel strain where you have this concrete strain multiplied with D minus X over X. Or you could also have the strain concrete, the compression steel concrete, compression steel strain, where you take this as a X over D dash over X. Okay, so this is the relationship. So determine the strain stresses in reinforcement can evaluate it from the stress strain curve with known steel strain depth, which is the X, the depth of your neutral axis from the top. Okay, and then you get this from D, which is the position. Okay, the position of the tendon. Okay, something like this to the mid height of the knee, and then you have your D. Okay, and then your strain, tensile strain, and then also your concrete ultimate strain. Okay, then you get your X. So the maximum compressive strain in the concrete is given, whereby 0.0035 for concrete class this, and then for more than 50 you have to refer to table 3.1 for the ultimate strain value. Okay, this is for lower than 50, you can take 0.0035 for the ultimate concrete strain. Okay, ultimate limit for F1K is equal to 500. For steel, you can say that it's around 0.00217. Okay, so the ultimate steel in tension is 0.0027. So when you have like you calculate the equation by putting the tension steel strain and also ultimate concrete strain, then you get 0.617 D. So D will remain based on the position of your bar. So in ensuring yielding of the tension, so you have it X is must be equal or lesser than 0.617 D for your neutral axis. So you mean X your neutral axis height. So at ultimate limit state, ULS member section inflection should be ductile. Okay, and that failure should occur with gradual yielding and of the tensile tension steel, not by sudden catastrophic compression failure of the concrete. Okay, so yielding of the reinforcement enables the formation of plastic hinge so that the distribution of maximum moment can occur. So resulting safer and economical structure. So therefore, EC2 limits the depth into the 0.5 D. So instead of taking 0.617 D, it limits the depth of your neutral axis to become X is equal or lesser than 0.45 D. Okay. So normally when you know the position of your bar, then you will be able to know what will be your position of your neutral axis. Okay, so for your pre-stressing steel, I think we talked about this a bit before this. So for pre-stressing steel, the properties, the stress is depend on 0.1% proof stress, and the specific value of the tensile strength, which is the FPK, are defined, which is this value. Characteristic value of the 0.1% proof load and the characteristic maximum load in axial. So by dividing the normal nominal cross-section area. Okay. So you have this one is FPK lah. This is the tensile strength. And then this is the proof stress. Okay. So you know that the proof stress is a bit lower than the tensile strength of a steel. So you have the ultimate the strength. Okay, so this is also to show the the position of the what is the ultimate strength and then what is the proof strength. Okay, so this method may be applied to a cross section of any shape which may have an arrangement of pre-stressing wires or tendons. Okay, so you can apply this arrangement. So use the stress strain curve for the pre-stressing steel, figure 3.0, 10 of code, to calculate tension force in each layer of steel. It depends on how many layers steel that you have. Okay, so the total steel strain is that due to bending added to the initial strain in the steel resulting from the stress, pre-stress. So you have the actual coming from the the reinforcement itself, and then you have additional where it comes from pre-stress value. Okay, and then for a series of assumed neutral axis position, the total capacity, assume natural axis position, the total tension capacity is compared with compressive force developed by uniform stress of mu FCD. So when a reasonable agreement is obtained, the maximum resistance can be evaluated. So actually there is a try and error for this calculation because we don't know what is the neutral axis height, the x. Okay, that will provide this tension capacity equal to compressive force capacity. Okay, for example, because once it's equal, then it shows that that will be your maximum value for your moment resistance. Okay, so here is where this is the force of your steel Fs equal to the strength multiplied with the area, and then this is the force for your concrete, which is your mu times the strength times with the B times with the lambda times with the x. So you are kind of like you have this one is lambda x, so this is actually your mu FCD B. Okay, and then this one you multiply these two as an area, you will get your FC value. So assume x. How to assume your x is by checking Fs must equal to Fc. So then your mu is equal to your moment, ultimate moment of your steel, Fs multiplied with Z, and also ultimate moment if Fc multiplied with Z. So you will get this equation. Okay, sekejap, ada tak ikut tak? Oh, tak ada. Nanti later on I will show you in detail lah how this is actually taken into consideration. Okay, because moment is calculated when you have Fc multiplied with Z at this direction. Okay, and also Fs multiplied with Z. So this will be your moment. Okay, acting on the what we call that, under the stress block. Okay, so yeah, that's about it. I think that's all. I wanna stop here because I don't wanna proceed with the examples. Later on next week I will proceed with the example because this example I will need full concentration. So I will cover it in your 1 hour lecture next week. Okay, all right. So then it will be covered in your 1 hour lecture. So 2 hours. So for you guys to prepare, I want you to at least go through the example at home. Okay, at least you have some idea what is the calculation is all about and things like that. Okay, and forces in steel, and then the additional reinforcement and okay, it's not that difficult. It's actually very straightforward. I think it's not something that you are not familiar with. It's something that you are familiar with. Okay, just if you so I want you on the lecture that we have gone through today. Okay, try recall back what you have done in your RC design. Okay, how you get the moment, you know, the stress block value and so on. So try to recall back. Okay, in your I will later on, maybe I will try to think something that can help you in terms of recalling your RC design stress block. Okay, and at least when we go through this example next week, you have some idea, you know, how the the calculation of to check your ultimate resistance moment for your pre-stress pin. Okay, any questions so far before we end? Aina? Ana Shakira, okay?
Okay, madam. Okay.
Okay, ya. Hairunisa, okay?
Okay, madam.
Right, no Ain, Farisha? Okay, Sukri, okay?
Okay, madam.
Alright, yeah. So I think I hope I explained it to you well, hopefully, and you guys are clear. Because what we are talking about mostly about, you know, the properties or the stress strain of the behavior or behavior of the material. Means that we have concrete, we have steel, and also we have pre-stress tendon properties. So steel reinforcement and tendon are two different properties, you know, unless your what you call that, you are using bar as your tendon, but still you will give you another additional strain because you pull your bar. Okay, so in terms of material, probably the same type of material, but you still have initial strain because you pull the bar, so you are applying force to that bar. So exactly, so in a way, when you want to design or you want to check, calculate your moment, you have to include or treat it as a tendon. Okay. Alright, so I think if there's no question, so I end today's class with the notes first, and then next week, inshallah, alright, with Allah wills, we continue with the examples. Okay, you can check the notes and then can go through the example first before I explain next week. Okay, we will go through like try to go through it one by one, so that you have you know, a clear understanding of how you want to calculate your ultimate resistance moment for your design. Okay, all right, so I think if there's no further question, I think that's all from me. Okay, study for your test next week. Next week, right? This week or next week?
This week, madam.
Oh, this week kan? Dah lupa macam this week. Okay, study for your test this week. Okay, your Magnell diagram, or because it will be until your Magnell diagram calculation. So the topic theoretical part. Okay, even try to make sure that, you know, the theoretical part too you cover, because it's a waste if you didn't read or go through the theoretical part. I know you have to do a little bit memorizing here and there. I hope with the things that we have discussed, at least make your, you know, the process of try to memorize your, you know, the understanding the theoretical part much easier, and it helps you in terms of answering question in your test, inshallah. Okay. What else? It is important, yeah, because we don't have final. So don't take for granted your test, even though it's been done online. Okay, we don't have final, so your test is quite, you know, you have only 2 tests. Okay, so with 2 tests, actually, you have 2 tests, right? Yeah, you have 2 tests. Okay, we have 1 test. I forgot already. With so many changes, you know, during online. Okay, but then what we call that, because we don't have the 60% of your final exam, so you have to really do well in your test. Okay, so if you have any question before that, I will try to assist. Okay, so with that, thank you very much. Okay, for those who are here live with me, and as I always say, I really appreciate students who spend your time, try to be here live together with me. Okay, we have like around 18 students. Okay, not bad. Normally I have for this class more than 18. Okay, I don't know, maybe today, maybe it's a morning class. I don't know why. Where are the rest? So hopefully to see others later. I mean, maybe next week or in our next lecture, inshallah. Okay, so thank you very much. Okay, so I wish you stay safe, study well for your test, and I think I'll be seeing you back in our lecture next week, inshallah. Okay, with that, thank you very much. Assalamualaikum warahmatullah. See you back. Take care. Stay
Thank
safe.
you, madam.
Thank you,
Okay,
madam.
salam
Thank you,
Ramadan ya.
Thank you,
madam.
madam.
Buka puasa elok-elok.
Thank you, madam.
Okay.
Madam
Thank you,
pun.
madam.
Madam.
Thank you.
Get well soon, madam.
Oh, thank you. The thing is on and off. Flu. Thank you.